Okay, so the plan for class today is to start sections 15.1 and 15.2. We'll kind of do a little bit of both of the sections, and then the supplement for this week will be to finish both 15.1 and 15.2. So doing a little bit more work, rounding out a little bit of 15.1 and doing some other examples maybe in 15.2. Note that there is no class Wednesday for the Juneteenth holiday, so it's a bit of a lighter week this week, just through sections 15.1 and 15.2 for this entire week. Next week, so the week of the 24th through the 30th, is the midterm exam. So I posted the sample exam yesterday. I think I posted that, and the Examity practice exam as well. And earlier today, I posted an announcement kind of explaining the process a little bit with the Examity practice exam. So Examity is the third-party automated proctoring system. So that's kind of something that I would strongly recommend getting set up this week. It is a little bit of a later week. That should give you a little bit more margin. So yeah, so getting into your Examity account, getting kind of the account set up correctly, your ID entered and all of that kind of stuff. Strongly recommend doing that this week, making sure everything goes well, and then also completing the Examity practice exam, which again, just kind of walks you through. It's really just meant to walk you through the steps of taking an exam on WebAssign with Examity. And then next week, the actual midterm will be live. So that'll go live at 9 a.m. on the 24th on Monday, and it will be due at 11:59 p.m. on Sunday the 30th. I strongly recommend that you do not wait until the last minute to take the midterm exam. I recommend planning to take it Thursday or earlier in the week. And that's because, well, for a few reasons. One, if you plan to take it, say, Saturday or Sunday, and something strange happens, you have an internet problem or a tech problem or something, there's less support available, and there's that doesn't leave you much of a buffer to get the exam completed before the deadline. And the other thing is that some students have really pushed it and waited until, almost literally the last minute to take it. And sometimes that just causes, there are just little glitches with just edge cases. Like if you log into Examity and it, thinks you don't have enough time to take the exam, it might not even let you start, things like that. So I try to kind of push the Examity window out a little bit further. I think I set it to something like 1:30 a.m. or 2 a.m. on Monday so that it doesn't do that. But then, some students see that and get a little confused. So just plan to take the exam, Thursday, I would say Friday at the latest. And then if something does go wrong, you've got a couple-day buffer. And that also avoids all of those edge cases. Okay, so with that being said, are there any questions on any of this administrative material for the next couple weeks? Oh, and I'll send out another announcement in a couple of days about the midterm exam, so just some more details about the exam itself. But I like to send out the Examity practice exam announcement and give it a couple of days before sending out another announcement, just so everything's not coming in at once. Okay. So I think that is the administrative bookkeeping I wanted to get through. Just remember, no class Wednesday. And then focus on the Examity practice exam for the second half of this week. So the plan is to start chapter 15, to start kind of another big shift in focus. We were just in chapter 14, which was kind of all about derivatives. And that kind of mirrors, I guess, in a sense, kind of in Calc 1 and Stewart anyway, like chapters 3 and 4, a lot of different applications and rules for derivatives. And then Stewart in chapters 5 and 6 kind of jumps over to integration. And that's kind of the switch that we're making now. So we're going to be looking at double integrals over rectangles and over general regions. So we're looking at integration, but with respect to functions of multiple variables. So let's take a brief look back at integration from Calc 1. So let's look at example 0 here, and we'll just kind of try to remember some of these ideas from Calc 1. This should all be pretty familiar to you, especially, with Calc 2 probably being pretty fresh in most of your minds, but just to kind of recall some of these ideas, and then we're going to see how this transfers over to the multidimensional case. So consider this example. Find the area between the curve y equals 4 minus x squared and the x-axis for x in 0 to 1. And so we're looking for this area. We know that the integral represents the area. Let me zoom this in a little bit. There we go. And we remember the way that we approach this problem was we said, well, I can approximate this area by splitting up my interval from 0 to 1 into n subintervals. On each subinterval, instead of looking at the height of it at the top edge of that interval of that two-dimensional structure as the curve, which it's complicated to find that area of that little area that has 3 flat sides and 1 curved side. Instead, I'm just going to make a box where the height of the box is approximately the height of the curve. Maybe I take the right endpoint and match the height of the box to the right endpoint, to the curve at the right endpoint, or at the left endpoint, or the midpoint, but it doesn't much matter. And I do that with each of these. Each of these subintervals. And I can look at the sum of the areas of these boxes, which are easy to compute. And I can see that that's going to be an approximation to the total area under the curve. I can also see that as I use more boxes, as I refine my partition, say I'm using right endpoints here, the error that I make, in this case, I underestimated in each case just because of the fact that I was using right endpoints and this is a decreasing function. I see the error that I make, or in other words, how much white space is above the blocks and below the curves, it gets cut down when I refine my estimate. When I use more boxes, I cut down the amount of error that I make. So the more boxes I use, the better my approximation, and we define the integral as the limit of this process. So we take, in this case, say x naught equals 0 and xn equal 1, and then we have subintervals that go from, say, xi to xi plus 1. So here we'll define x sub I equals a plus I delta x, where delta x is b minus a over n. We'll only look at the case where we have equally sized subintervals. It's actually not crucial that that is true, but that just makes a lot of our discussion easier to stick to that case. We could use different size subintervals, and there are actually some applications where that is a very important thing to be able to do, but for our purposes, we'll just look at equal size subintervals. So we let delta x be b minus a over n. Xi is a plus I delta x. So for instance, x0 is a, and xn is, well, when I is n, that's just a plus b minus a, that's just b. So if we're looking at a general interval going from a to b, this is how we would define our delta x and our xi's. And we can see that our area under our curve is approximately, well, we're adding up for, say, I equals 1 to n, or I guess I used k in my notes. Let me just stick with k. So summing up, k equals 1 to n of each of these areas of the boxes. So this is f of xk star times delta x. So for some input, we take the height of our box to be the output of the function for that input, and then we multiply by the base width. So that's base times height. That's for each box, and then we add those up to get an approximation to our area under the curve. And this xk star can be anywhere in the subinterval. So it could be, let me say that this is the subinterval, the kth subinterval. It could be the left endpoint. It could be the right endpoint. It could be somewhere in the middle. You could actually even choose it randomly from one interval to the next, and all of this still works. But typically if we were going to get an estimate, we would choose them all at the right endpoint or all at the left endpoint, or maybe all in the middle. Those would be the typical choices that we might want to make. And then we say that the integral from a to b, f of x dx, i.e. the signed area under the curve, or the signed area between the curve and the x-axis, and between x equals a and x equals b, is the limit as n goes to infinity of this process. Sum k equals 1 to n, f of xk star delta x. So we make these boxes skinnier and skinnier. That refines our estimate. And in the limit, we say that it's equal. So this is the idea of a Riemann sum and Riemann integration. We do know that it's a typical kind of Calc 1 problem to do one example using the limit of the integral to argue what the area has to be. But we do know that this is typically very, very difficult to use, even more difficult than using the definition of the derivative to compute a derivative. We have a major theorem that saves the day, fundamental theorem of calculus, and typically what I'm going to say is listed as the second part of the fundamental theorem of calculus. So fundamental theorem of calculus part 2, if f is continuous on AB, then integral a to b f of x dx equals big F at b minus big F at a. I'm doing a poor job of planning out my spacing today. It's equal to this, where big F prime of x equals little f of x, where big F is any antiderivative of little f. So in practice, we compute definite integrals almost exclusively using the fundamental theorem of calculus. We try to figure out a function for which, when we differentiate it, we get our integrand, and then we just evaluate that function. And then, of course, we have a bunch of tricks. We have things like substitution, integration by parts, partial fractions, all of these kinds of tricks that we learn in Calc 2 that are helpful in finding antiderivatives and evaluating integrals. Okay, so coming back to our problem, now I think we're ready to answer our question. What is this area? Well, this is integral 0 to 1 4 minus x squared dx. And to anti-differentiate this, we get 4x minus 4a power function. We add 1 to the power, we divide by the new power. And we evaluate this from 0 to 1, which is often just written in this abbreviated form with kind of square brackets around the thing that we're evaluating, and then an upper and a lower bound. So we evaluate at 1 and we subtract off the evaluation at 0. Or this is just 4 minus 1/3, and then minus 0 minus 0. This is, what is it, 23 over 3, I guess. Yeah. Oh, brain fart. 11 over 3. I don't know why I was thinking of 8 minus 1/3. Okay, so that is our uh, super quick crash course review of basic integration. And one more point that I would like to make quickly here. If we were to say, look at, so this is just another example, call it 0.5. If we were to look at something like integral minus 1 to 1 of, say, 4 minus x squared dx, we know we can break this into three integrals. And we can leverage some properties here. So the first is if we integrate a constant over a region, we just get the size of the region times the constant as the output. So I integrate height 4 over width from minus 1 to 1 is 2. This gives me 8. If I integrate an odd function where f of minus x equals minus f of x over a symmetric interval, an interval that's symmetric about 0, provided my function is integrable in the first place, I wouldn't want to do this for, say, integrating 1 over x between minus 1 and 1. But something like this, we have no problem with integration. Provided that my integrand is integrable over that region, minus 1 to 1, then this turns out to be 0. Integrate an odd function over a symmetric region, we get 0. And if we integrate an even function, where f of minus x equals just f of x, where the function gets rid of negatives, if we integrate an even function over a symmetric region, we can just double the integral on one side of that region. So integrating a constant, an odd function, an even function, these are some tricks we can do to make things a little easier on ourselves. And of course, this gives us 1/3 x cubed from 0 to 1 is 1/3 times 2 times -2, -2/3. Okay, so I think that was all that I wanted to discuss in the crash course for single variable integration. Are there any questions on any of this? Okay, so now we're going to move to double integrals. We're going to look at extending these ideas to two-dimensional domains. So we're starting with just functions of two variables for now. Okay, so in 1D, what were the ideas that we had? We had an interval a to b of interest, and we broke that interval into some subintervals. And on those subintervals, we wanted to evaluate our function. We wanted to evaluate our function to give us the height of these Riemann boxes. So that was the 1D idea. What about in 2D? I'm going to try to draw this fairly nicely. So in 2D, my function is going to be represented by a surface. Let's say we have a surface that's kind of like in the first octant, a quadratic that's kind of opening downwards. So we have something like this. In the YZ plane, something like this. In the XZ plane. And then coming out, say, at a 45-degree angle, something like that. So we have this kind of, like a quarter of an umbrella kind of a shaped thing. So we have the surface here that is above the XY plane, and it's above a certain region in the XY plane, maybe like a rectangle. So over here, I had, say, a region of interest, A to B. And over here, I have a region of interest that's maybe, for instance, a rectangle in the XY plane. So I can take this rectangle in the XY plane, and it doesn't always have to be a rectangle, but for now, we'll be focusing on rectangles. This rectangle in the XY plane is kind of analogous to that line segment from A to B over there. Maybe X goes from, say, A to B, and Y from, say, C to D. And I can imagine partitioning the X-axis into a bunch of subintervals, and the same with the Y-axis. They might be a different number of subintervals. They might be different size intervals for the X and the Y. But I see effectively what this does is it partitions my big rectangle, A to B and then C to D, into a bunch of small rectangles. Like, say, this one, for instance. This is some small little rectangular chunk. Maybe it corresponds to, say, a rectangle here. Now, when I think of a 1D function and I say, does the integral of that function from A to B represent? If the function is positive, we think of it as just being the area between the curve and the x-axis. What do I think this integral is going to represent over here? Well, I think it's going to be, for a positive function anyway, the maybe volume, because we've stepped up one dimension, between the surface and the xy plane. So if I imagine kind of coming straight up, making a kind of rectangular column here. Now, I suppose if I wanted the exact volume, I would have to have a column that has a flat bottom, 4 flat sides, but then the top would be kind of curved because where it intersects the surface is going to be a curve. But I can approximate this by, say, letting it intersect the surface at some point, and then just taking the height across this entire box to be estimated by that particular function output at that point. So here it looks like maybe I was taking the point closest to the origin as the proxy for the height of the box, and then just pretending that on that whole red rectangle, the function is just about that high everywhere. If my rectangles are pretty small, there should be a pretty good approximation. And in the limit, as I let the number of rectangles go to infinity, this should should move from an approximation to an exact value. So it's a little hard to see. My box isn't drawn very, very nicely over here, but imagine just the rectangular column going up, intersecting that surface at one point, and then just having a nice flat top that's parallel to the XY plane. So that gives me a little component of volume. It's going to look something like, well, I might have a delta X and a delta Y. So my base area is going to be delta X times delta Y. My little chunk of area in my domain space is going to look like delta X times delta Y. And then I need to multiply that by height to get the volume of this one little cuboid. So what's the height going to be? It's going to be something like f of xk star yk star. And then if I want the total volume between the surface and the xy plane, That's going to be approximately the sum k equals 1 to, let's call it n or whatever, where I'm just adding up all of these n boxes here. So this would be like box 1 and box 2, all the way up here to box n. So I'm adding them up however I add them up. I don't know, maybe left to right and kind of just going left to right and then go up a level, go left to right again, and so on. So that will be my approximation for the volume. And I think that as n goes to infinity, as my boxes all get smaller and smaller and I get more and more of them, I think that as n goes to infinity, the approximately equal to goes to exactly equal to. I'll just kind of write it that way. I think my approximation for the volume turns into an exact representation of the volume. Okay, so let's think about a couple of practical points here. So how can I go through and count up all of these boxes? The first thing I might realize is I could kind of count them in some kind of haphazard way like this, but I could also be a little bit more ordered about things. And I could say, well, let me look at my x's here. Let me get rid of this 1 and 2 and so on. I'm going to call this maybe x naught and x1, x2, and so on out to, and what name did I give it in my notes? X n. And then for the y's, I'll have y naught. Why not sounds like, why not call it why not? Y1, Y2, out through Ym. And this height we'll call delta Y, and this width we'll call delta X. I know that's probably a little bit small. I'm writing a lot of subscripts and things, but I note that I could approach counting these if I want to do it in a more orderly fashion, maybe in two different ways. I could say start with my I'm trying to make this a little bit smaller. There we go. Start with my boxes that are between y0 and y1 and kind of add all of those up. When I do that, that's going to give me some estimate for volume. I'm adding up the, box one's corresponding approximation to volume, right? It's base area times height, and the same for box 2 and for 3 and so on. That's going to give me a volume that corresponds to a certain y value. So maybe this is like volume corresponding to y1 or something like that. And then after that, I can add up the next line. And this would give me something like a volume corresponding to y2. So an approximation to the overall volume, but just that slice where we're going along a specific y coordinate in the domain. And then we could go along the third row. That would give me v of, say, a y3, v of y4, v of y5, and so on. So I could add across the rows first. That's going to be holding a y number fixed, and then adding up across all of the x's. And then if I want a total volume, I would take the sum of all of these. So I then kind of, in a sense, have a column of sums of rows, and I add down the column. But notice I could also add in a similar way. I could have added columns first. I could have added this column first, and it would be something like a volume corresponding to, say, x1. When I add across all of those, when I add down that first column, all the elements of that column that correspond to, something like just to the left of x1. I could have done the same for the second column. And the third, and so on. And then I have a bunch of sums of columns in a row, and I could sum across that row, so to speak, to again get the total summation of all of the little cuboid volumes. These should be equal to one another because all that I did is count one direction or the other direction first, and there's a finite number of them. So I'm not counting infinitely many things like where something like the Riemann rearrangement theorem or something might come into play. I'm counting finitely many things. It shouldn't matter what order I count them in. So when I think of coming down here, I could say that my volume could be something like I equal 1 to n, some j equals 1 to m of what? F of, say, x I star yj star delta x delta y. Or I could think of this as being some j equals 1 to m, some I equals 1 to n, f of xi star yj star delta x delta y. So what am I doing here? I'm taking this single sum and I'm actually breaking it into a double sum. So this inner sum, what does it do? Well, this sums up the different y's for a specific x. This is like a green column. And then this outer sum sums up all of the columns. So this is like the blue sum up there. Or in the second representation, what am I doing here? The I is changing, which means the y's are fixed. That means summing across the rows as I vary x. That's like getting one of the red rows for each I equals 1, I equals 2, and so on. Or sorry, for each j equals 1 and 2, and so on. And then I sum across all of my j's. I sum up this red column. Okay, so I think at this point we are ready to jump down to these. Oh, and there's one more point that I want to make. I want to make an analogy to the disk and shell method. From Calc 2. So if you think of, say, you have some solid of rotation, let's say it's something like a sphere. We can think of this as being like a circle. Rotated about one axis. And for these solids of rotation in Calc 2, we had a way to figure out their volume. We would take, let me draw this a little bit more nicely. I'll just draw the upper half of the sphere. we would take a plane and intersect the plane with that solid, and we would get a cross-sectional area. And then what would we do? We would just integrate that cross-sectional area. We would think of building up this sphere using a bunch of what we might have called at the time washers, a bunch of things that looked kind of like say little coins like quarters or dimes or something like that, and then just stacking them up on top of one another to build up a sphere like this. So this idea of taking a cross-sectional area of a solid and then stacking cross-sectional areas is an idea that we've already seen before. Okay, so I think at this point, we can just jump into the definition, and this should make this definition make a bit more sense. So the double integral of f of xy, so a function with two inputs, one output, over a rectangle R, where x is between a and b, y is between c and d, is defined as follows. We give it this symbol. We give it two integral signs to represent that we're integrating a function of two variables, two input variables. We're integrating over a region, R, the rectangle, and our integrand, our function is, if I can select it here, doesn't want to let me select it, but our function is f of xy. Our, in a sense, variable of integration, in a sense, is dA here. So what do we mean by that? Well, over in our 1D case, we had a delta x that represented the increment in the independent variable space. It was kind of our base width that we multiplied by height. Over here, our increment in our independent variable space is actually a little chunk of area. It's a little two-dimensional chunk representing a small variation in x as well as a small variation in y. So this is a little chunk of area we call dA. And of course, this delta A is going to be delta x times delta y. So we'll see that idea come up a little bit later. So this dA represents that little chunk of area. We define this to be a limit of a Riemann sum, just like before. We have some I equals 1 to m, j equals 1 to n of, and here I use notation that I think is from the book, x sub ij star comma y sub ij star times delta A times delta x times delta y. And here again, the xij star, yij star is just some point that's chosen anywhere in the I comma j rectangle. Anywhere in that rectangle, we can choose the point that acts as the representative point where we evaluate the function and set the height of the function above that rectangle. Okay, so a theorem, Fubini's theorem, super helpful. If f is continuous on the rectangle R, then this double integral, we could represent it in two different ways. We could integrate dy first, and then integrate that dx. So I could choose to do integral from y equals c to d, f of x comma y dy, which it's not really letting me select. Having lots of formatting issues in this one for some reason. I think it's all these integral signs. I was messing with this for quite a while this afternoon, trying to get the integrals to look right. So integral y equals c to d, f of x y dy, that's a little, in a sense, a chunk of volume, an infinitesimal chunk of volume now, but kind of a chunk of volume. where we're varying y but holding x constant. If we're varying y but holding x constant, that's kind of like the columns up here. That's like a little chunk of volume corresponding to x. But since it's infinitesimal, we might even call it an area instead of a volume, since we've shrunk the width down essentially to 0. So let's rename it, instead of volume, maybe area. And then what are we doing to that? Well, we're taking that thing and putting that into an integral, x equals a to b, of that thing dx. So we want to integrate x equals a to x equals b, a of x dx. Now keep in mind, when we're doing this y integral down here, we're thinking of x as being like a constant. So this is a similar idea to a partial derivative. We're taking kind of a partial integral in a sense here. We're integrating only in the y direction, keeping x constant, and then later on, we integrate in the x direction. And Fubini's theorem says that we could integrate y first, then x, or we could integrate x first, and then y. When we integrate x first, we're holding y constant, moving along x. That'll give me a little slice of area, or kind of an infinitesimal volume for a particular value of y. And then I kind of add up all of those contributions for all of the possible values of y. So it really has very much the same feel to this kind of disk method from Calc 2, looking at volumes of solids of revolution. Or kind of in very simple terms, we can interchange the order of integration. When we're integrating on a rectangle, that's a pretty straightforward thing to do. We'll see coming up here, when we're integrating on over a domain that's not a rectangle, it actually can be a little bit tricky. So we can't just kind of flip the two integral signs. We have to be careful how we do it. Okay, another theorem. Many of our theorems from single variable integrals hold here as well, but particularly a nice one is that double integrals are linear. In other words, constants can come out, and the integral of the sum is the sum of the integrals. So super nice one to be able to use. We can bring constants outside of the integral, outside of the double integral, and we can split double integrals apart. So double integral of f plus g is double integral f plus double integral g. And there's, several other theorems and properties and things as well, but I think these are the most useful. Okay, let's look at example 1 here. Let's evaluate this integral, double integral over the following rectangle of 3 plus 4y dA. And we want to use the rectangle r equals 0, 3 cross 0, 1. So this means x is between 0 and 3, and y is between 0 and 1. Right, by convention, we just always write x first. So what does this look like? Well, one thing that I notice about this integrand, 3 plus 4y, it has no x's in it explicitly. So if I know what the picture of this looks like in the yz plane, then I just kind of copy it over along the x-axis to get my surface. So in the yz plane, well, y goes from 0 to 1. So the y's I'm interested in go from 0 to 1. When y is 0, z is 3. When y is 1, z is 7. So I see it's just this straight line. It kind of makes a little trapezoid. So this is what it looks like in the YZ plane. But then x goes from 0 out to 3. And here this is 1 for y. Our region of interest, let me draw it first. Our region of interest is this region here. This is our rectangle. So this green line I drew here is in the YZ plane. But then the surface is going to just kind of trace straight out along the X axis. Like this. So it's a little bit like a kind of a slanted flat roof of like a lean-to shed kind of thing. And then I see that this is going to give me a volume between this surface, this kind of chunk of a plane in this case, and the XY plane. So this volume that this encloses is what I'm looking for. Well, one way that I can find this is pretty simple in this case. I can actually look for an area. This would be like a cross-sectional area, say when x is 0. So what would my area in this YZ plane, or really in any plane that's perpendicular to the x-axis, what would the area look like? It would look exactly the same as this because there's no explicit dependence on x. So for any x, what is my area going to be? It's going to be the area of this trapezoid, which is the average of the heights. 3 plus 7 is 10 over 2 is 5 times the base width, or just 5. Right? We can always get that from a trapezoid because the trick is you go halfway between the extremes, and this little triangle that you kind of have left over on top can flip over and fill in the void on the bottom. So the area of a trapezoid is 1/2 of base plus height times the width. But then what do I have to do? I have to take that cross-sectional area of 5 and kind of account for it across the entire x range from 0 to 3. So it's kind of like I'm just integrating from x's perspective a constant 5 over the interval 0 to 3. Well, if I integrate a constant over an interval, I just get the product of the constant times the length of the interval. So this just says that my volume is going to be 5, the constant, times the length of that interval from 0 to 3 is just 3 or 15. So this pure geometric argument says that, well, we think the volume that this double integral should be 15. Let's see if we can do this a different way. Can I interpret this double integral over the region as what we call an iterated integral? These integrals, when we think of them like this, we call them iterated integrals because we think of kind of doing one integral and then plugging the result of that into another integral. So we're kind of iterating the integration process. So how else could we approach this? Well, we could say, for instance, integral from y equals, well, y goes from 0 to 1. That's the integral of integral x equals, x goes from 0 to 3 of 3 plus 4y. And here I want to be careful. My inside integral is with respect to x, so I want to do dx. And then my outside integral is with respect to y, so dy comes second. I could also do this the opposite way. Integral x equals 0 to 3, integral y equals 0 to 1, 3 plus 4y, dy, dx now. The order of those last differentials changed because the inside integral is now y, and the outside is x. So we could set it up either way. I'll leave this as an exercise. But note that over here, what am I doing? I'm fixing an x and then letting y range. That's really more in line with the picture that I drew up here. So this exercise is really just kind of computing the result that I got from my picture and my cross-sectional area argument, but doing it in this integral framework. We should get the same answer if we do it the opposite way, if we kind of flipped our way of doing it and we varied along x first, and then computed those cross-sectional areas moving in the y direction. So again, I treat this like one integral being plugged into another integral. Now, when I do the x integral, at the end of that, I shouldn't have any x's left, but I typically will have y's left. And then I do the y integral on the outside, and then I shouldn't have any x's or y's left. Over here, when I do the y integral on the inside, when I finish that, I shouldn't have any y's left, but I, in general, can have x's left. I won't in this problem, but in general, I could. And then when I finish the x integral on the outside, I shouldn't have any x's or y's left. I should just have a number. Okay, so what is this inner integral here? Well, if I integrate this thing with respect to x, well, but wait, 3 plus 4y, that's just a constant with respect to x. I'm really just integrating a constant over an interval of length 3. That's just what that inside integral is. 3 plus 4y is a constant with respect to x. So I just multiply the integrand value by the interval width. Or that is the integral y equals 0 to 1 of 9 plus 12y dy. And at this point, I'm down to just the single variable calculus integral. This is 9y plus 6y squared from 0 to 1, just 9 plus 6 minus 0, and that is 15. So we do get agreement. So I think the first challenge in this chapter is really getting pretty good at visualizing these 3D shapes. I think it's really helpful to be able to get a picture in your mind of what's going on, not just of the input region, but also of the 3D shape in general. Even if you're not great at drawing, and I'm certainly not good at drawing, you can draw a drawing that's good enough to get you an idea of what the thing kind of looks like. Okay. So example 2, let's look at this example. Let's try to evaluate the double integral of e to the x times sine of 2y dA for this rectangle. X going between 0 and 1, y between 0 and pi over 2. So this is the, let me give myself a little more room between these. This is the iterated integral. Well, I could do, say, x equals 0 to 1, y equals 0 to pi over 2, e to the x, sine of 2y. And here my inner integral is with respect to y, so I'll do dy. Then dx is my outer integrals with respect to x. Now here, instead of really thinking geometrically, I'm going to try to think almost more purely algebraically. The first thing that I notice is that my inner integral is with respect to the variable y. It has some x's in it. But in fact, the x's that it has is this e to the x times a function of y. I just have what amounts to constant times function of y integrated dy. Well, that constant, in this case, e to the x, that constant with respect to y, well, that can just pop out in front of the integral, right? That can just come out as an integral x equal to 0 to 1 of e to the x times the integral y equals 0 to pi over 2 sine of 2y dy. And when I do this, because it starts to look a little messy, a lot of times I'll put in parentheses just to really kind of keep things sorted out. It's not strictly necessary, but I think it looks a little cleaner to put parentheses in there just to make it very clear that it's like e to the x times this integral, and that whole thing is being integrated dx. To my eye, it looks a little cleaner. It looks a little more obvious, but you can, do what works for you. So much of this chapter is just these little bookkeeping things, making sure you don't lose track of something or get something in the wrong place. But here what I notice is this is, well, what is this? This is an integral. Y goes from 0 to pi over 2 sine of 2y dy. This is actually just a number, right? It doesn't have any x's in it. It's not a function of x. It's just a number. It's a number like 3 or 7 or something like that. But from the perspective of this x integral x equals 0 to 1, e to the x times this thing dx, well, that number can just come out in front of the x integral. I actually could just do integral y equals 0 to pi over 2 sine 2y dy. That whole number just comes out in front of the x integral and multiplies it. And what have I actually done? I've actually split apart. I've kind of like disentangled my double integral, my iterated integral, into just two single variable integrals. Can I always do that? Up here, I suppose I could, right? Because this 3 plus 4y didn't depend on x. It could have come out of the x integral, and that would have allowed me to disentangle them. Can I do that all the time, though? Well, something like this, though, e to the x times y, e to the power x times y, well, that has a y in it, so it can't come out of the y integral, but it also has an x in it, so it needs to stay inside of the x integral as well. We can't always disentangle our integrals like this, but when we can, it's super helpful. Obviously, we just now have two Calc 1 problems to do, and that's probably going to be more straightforward than trying to do a full iterated integral. What was kind of the magic that made this happen? I could write this as f of x times g of y, or let me say h of x times g of y, since I already used f previously. So if I can write, say, f of xy equals h of x times g of y, where the h function has no y's in it and the g function has no x's, then I can disentangle my integrals. So if I recognize this, then I can leverage it and make my life a little bit easier. So this first integral sine of 2y, just is negative 1/2 cos of 2y, evaluated from 0 to pi over 2. And the second integral is just e to the x, evaluated from 0 to 1. Or this is negative 1/2 cos of pi, cos of 2 pi over 2. Cos of pi is negative 1, minus cos of 0 is minus 1. And then times e to the 1 minus e to the 0. So I have a negative 2 times negative 1/2 is just 1. This is just e minus 1. So if there's this kind of independence property where I can split my f of xy into h of x times g of y, I can disentangle my integrals, and importantly, on a region like this, I can disentangle my integrals and work with them individually. Okay, let's look at this integral here. Now, this is one that we cannot disentangle, like I mentioned before. What can we learn from this one? So if I look at this example, and I'm going to go a little more quickly through this than I had planned because I want to get through a little more of the lecture. We're going a little slower than I anticipated. If I think of what the procedure for this would look like, if I'm integrating with respect to y first, in this case, my integrand with respect to y is a little bit annoying. I need to integrate basically y e to the y. I would need to use integration by parts. What if I instead set this up the other way? Integral y equals 0 to 1 of the integral x equals 1 to 3, y e to the xy dx now dy. Well, now I realize, okay, I have the factor of y here. That's a constant with respect to x. It can come out in front of here. Okay, now I can integrate this e to the xy with respect to x. Here we're thinking of y as a constant, so e to the constant times x. If I integrate that, that's 1 over constant times e to the constant times x. And we're evaluating this from x equals 1 to 3. This is all integrated dy. Now again, 1 over y is a constant with respect to x, so it can actually come out in front, and it actually divides out with that factor of y. That's pretty nice. So e to the x times y when x equals 3 is e to the 3y minus e to the x times y when x equals 1 is e to the y. I finished my x integral. It's a definite integral. I shouldn't have any x's left, and I don't have any x's left. That's always a good thing to check when you're partway through. If there's still an x floating around somewhere I missed a substitution or something. Now this integral is pretty easy to do, right? By switching the order, the integrand just cooperated a little better with the x integral, and then what was left over was easier to do in the y integral than if I had done it the other way. I could have done it the other way. If you want to practice your integration by parts, try it the original way and see if you can get the same answer. There is a little integral trick you need to get. You need to know to get through one point, but if you don't recognize the function as the derivative of some particular function, then plug it into Wolfram or something and it'll spit out the answer, but it's an e to the x over x kind of deal. Okay, but to finish this off, we integrate this function dy, 1/3 e to the 3y minus e to the y, evaluated from y equals 0 to 1. So this is what, 1/3 e cubed minus e. That's when we plug in y equals 1, and then subtract off 1/3 e to the 0 is 1 minus 1. And we could simplify this a little bit, I suppose, but that's what we get. Any questions on anything so far? And again, just be careful with the little stuff, right? I mean, when you get to the end, you've done all of this integration and all of this Calc 3 work. It's super easy to do things like, we're so used to having polynomials that we're evaluating. It's so easy to just like plug in y equals 0 and think that that just turns out to be all 0 instead of like the 1/3 minus 1. It's super easy to make little mistakes like that when there is so much else going on. Okay, and then lastly, let's look at this example. Lastly, in this section, let's look at this example double integral over, could we have separated the e term and this e to the xy? So the e to the xy is really stuck together. If we had something like e to the x plus y, that would be e to the x times e to the y. And then absolutely, and then we could absolutely split them into two integrals. So if we had instead, let's say, yeah, so that's a very good point. If we had integral x equals 1 to 3, integral y equals 0 to 1, if this was y e to the x plus y, dy dx, this integrand would be y e to the y times e to the x. And then absolutely, we would be able to disentangle the two and just do two single variable integrals and multiply the results together. Yeah, so that is a very good point. But as it stands here, e to the xy, that's kind of like too entangled. We can't really split that apart. So we have to do it as an iterated integral, either one direction or the other. This is by far the easier direction. You could do it the other direction, but again, even if you do the integration by parts, you kind of hit a sticking point where you have some e to the x over x's and things that you need to integrate, and they can be tricky to figure out how to integrate. Okay, so this example, double integral over this rectangular region, and when you see an interval squared, what that means is just each of the variables x and y are in that same interval. So it's like the square or rectangle from -1 to 1 on both axes. So our domain of interest is this rectangle like this, or square in this case. And I want to integrate xy squared plus cosine of y dA. So if I integrate, say, x equals -1 to 1, y equals -1 to 1 of xy squared plus cosine of y, and then I'll do dy dx. This one, it doesn't matter a whole lot which one you do first or second. So I'll start with this inside integral with respect to y. I can integrate xy squared with respect to y and get 1/3 xy cubed, and then integrate cosine of y with respect to y and get sine y. And I'm going to evaluate that from y equals -1 to +1. And that whole thing, I'm going to have gotten rid of all the y's when I do my evaluation, but there will still be some x's floating around. That whole thing, that whole function of x, I'll integrate dx. So x equals -1 to 1. And when y is +1, this gives me 1/3 x. 1 cubed is 1, plus sine of 1. And then minus when y is -1. But when y is -1, I get -1 cubed is also -1, so that's a plus 1/3 x. And then sine of -1, sine is an odd function, so sine of -1 is minus sine of 1. And I'm subtracting that off, so that's again plus sine of 1 dx. Actually, see, I kind of get the same thing twice. Turns out that there's some symmetry here, and we're either going to look at that at the end of today's lecture or as part of the supplement. So integral x equals -1 to 1 of 2/3 x plus 2 sine of 1 dx. And now we've actually made it down to a single variable integral. We can leverage all of our stuff we know from single variable calc, and here I will make use of the symmetry. This is an odd function being integrated over a symmetric interval. The first bit has got to be 0. And it's, of course, integrable. It's just a power function. And the second bit is just the constant being integrated over an interval. The constant is 2 sine of 1, and the interval has length 2 from -1 to 1. So that's 4 sine of 1, and that is our answer. So once we get down to a single variable integral, we can use all of our Calc 1 and Calc 2 tricks. When we have an iterated integral like this one up here, you might have sensed that, it seems like there's some symmetry going on because we got kind of two of the same thing. And there is, and we can look at some symmetries in 2 dimensions a little bit later. Any questions so far?
Why isn't a negative one on the sign to the right of the 1/3 x plus sine 1? Like, why isn't that a
This one
negative?
here?
Yeah.
Okay, so we're subtracting off the sign of -1 like that, but sine is an odd function. So sine of negative x equals negative sine of x. So this -1, the negative can come out in front of the sign and it's a sine of 1. And then I have a negative times the negative gives me a positive sine of positive 1. Yeah, good question though.
Okay, that makes sense. I think I just missed that.
Yeah, you have to use this little kind of trig property here. Cosine is an even function and sine is an odd function. Sine is symmetric when you rotate it about the origin 180 degrees, and cosine is symmetric when you flip it about the y-axis. So, yeah, there's a saying in either math or physics, or probably both, that when there's symmetry in a problem, it usually pays off to respect that symmetry, to try to use that symmetry in some way. So I use the symmetry a bit in that case here, using the fact that it's an odd function, and again down here, using the fact that 2/3 x is an odd function. And we could have even leveraged the symmetry even more all the way back up here to make an argument about this inside integral, although we would have to think about what it means to be symmetric in 2 dimensions and how that would all work out. Yeah, good question though. Okay, so moving on to the next idea. What if I have, instead of a region that is just a nice rectangular box, what if I have some wonky region like this? It's not a rectangle. I mean, it makes sense that we should still be able to talk about this wonky region and whatever the surface is that's above that region and the corresponding volume between that surface and, say, the xy plane. That still seems like a sensible question to try to address. But it's just that we don't have a nice rectangular box to work with anymore. The book goes into a bit of detail about some of the nuances and how you kind of just take this wonky region and embed it in a box, and then all of the theory from the over rectangular region just kind of ports over pretty nicely. So the theory still holds. We can still, exchange order of integrals and things like that. All of the theoretical ideas still hold. But the practical application sometimes is a little more challenging. In fact, is a lot of times a little more challenging. So let's look at this example. Let's integrate the function x squared y dA for x between 0 and 3. And, well, this looks a little strange. Y goes between 0 and x squared. When we had something like this, it was really very clear what our domain was, what our region of interest was. We let x vary between 2 numbers, y vary between 2 numbers. That gave us a rectangle. But here I have to really, I just have to draw out the picture. I usually start with the more complicated of them, and because y goes from 0 to x squared, I'm going to start with that. So I know that y starts at 0 at the x-axis, and it has an upper bound of y equals x squared. And then x ranges from x equals 0 to x equals 3. So this is actually my domain, my little region of interest. This is what we'll be laying on the xy plane, whereas x and y, and it goes something like this. And then my surface would be up above here, whatever it looks like. And then I would be looking for that volume under that surface above the xy plane. Okay, so what would an integral like this look like? An iterated integral? Well, I need to end up with a number out of this, right? If I think what is being asked here, we're asking for this particular volume. This should be a number. It shouldn't be like a function of x or a function of y that I get out. So if I make my inside integral, the integral from y equals 0 to x squared, what do I mean by that? What I mean by is that if I start by choosing a particular x to focus on, and then I take a cross-sectional area, the cross-sectional area is going to go from y equals 0 up to y equals x squared for that particular value of x. That's going to be the range of the contribution for that cross-sectional area. If I pick a different x, I'm going to get a different range along which I'm getting a contribution for the cross-sectional area. So I start by adding up along these kind of columns in a sense, going from the bottom curve to the top curve, or from just x equals 0 up to, or sorry, y equals 0 up to y equals x squared. And I'm integrating dy. I'm allowing y to vary while x is held constant here. But that gives me a bunch of cross-sectional areas, and I need to add those up going left to right, going along the row of cross-sectional areas. I can think of, each of these cross-sectional areas as being a number that's been kind of pushed down here, and then I want to add in the x direction. I need to integrate along the x direction, and I have contributions that range from x equals 0 to x equals 3 dx. Okay, so if I want to integrate x squared y dy, now one thing I might be tempted to do here is to try to completely separate these integrals, right? To make this like integral of, say, x squared dx times integral of y dy, this integrand is amenable to that. However, because I have a complicated region of integration, the region isn't amenable to that. So because I have this x squared as one of the bounds of integration of my dy integral, that dy integral has to stay inside the x integral, because that x squared at the top has to ultimately get integrated away. For a lot of these fairly simple mistakes that you can make, like trying to split apart integrals like this, if you did that, you would end up with some x's left over at the end, and you say, wait, I'm supposed to get just a number left over at the end. If you end up with variables left over at the end floating around for a definite integral like this, then you know something went wrong, and just go back and check that every step is actually valid. But here, if I'm integrating dy, I have x squared times, well, y integrates to 1/2 y squared, and y ranges from 0 to x squared. The mechanics are all the same as before. It just looks a little funny to have an x squared in one of the bounds of integration. But what did I do before? I said, well, my variable of interest was y. So I plug in the upper bound into y. So I have an x squared over 2 times, well, y squared, but I plug x squared into there. So I get x squared squared, x to the 4th, minus the same thing with y equals 0, but that's just a 0. Or this is integral x equals 0 to 3, 1/2 x to the 6 dx. And here, this is an easy integral to do. This is x to the 7 over 7, so 1/14, x to the 7th from x equals 0 to 3, and that is 3 to the 7th over 14. So here we integrated y on the inside and x on the outside. So we did the dy first and then the dx. Or we kind of held x constant, allowed y to vary. We kind of added down all of the columns. And then we added across the remaining row, the row that represented each column sum, in a sense. Could I have done it the opposite way? Sure, I could have. I'm going to redraw it because I've already drawn a little too much on that one. What did my region look like? Looked like this. Be really careful. It's not this part. Sometimes it's easy to make a mistake and get kind of the, in a sense, the wrong side of the rectangle. Y ranges between 0 and x squared, not say between x squared and what would it be, 9. So if y went from x squared to 9, that would be this other side up here, but that's not what we have. So just be a little careful. We do have this region down here. If I wanted to go the other direction, if I wanted to say add across the rows first, get row sums in a sense, and then add down that column, I would be holding y constant and then letting x vary, integrating across x. So if I wanted to go this route, maybe I'll scroll over here actually. I would be integrating some stuff dx with x going from something to something. And then what I would have coming out of there is effectively a bunch of row sums, a bunch of horizontal cross sections, horizontal in the direction that we're looking at it here in the domain space. But then I need to add those vertically. I need to add those along the y-axis. Now I can see that once I say for a particular y, what is my, in a sense, row sum, what is my integral with respect to x, then the y's that I add up are all of the y's ranging from 0 to 9, which is the highest output that we get here. So y goes from 0 to 9 now. Note that we didn't see that y equals 9 anywhere in this original setup over here. We had to deduce that from saying, well, for the function y equals x squared, when I plug in x equals 3, that's the highest output that I get as a y equals 9. And then when I look at my, in a sense, row sums, oops, those start at my curve and go up to x equals 3. So these have an upper bound of x equals 3 and a lower bound of Well, if y is x squared, x equals square root of y. My integrand is still the same. Nothing has changed with my integrand. It's still x squared y. But now we're integrating with respect to x first, and then with respect to y. And if I wanted to here, I can say, well, y is a constant with respect to x, so I can actually bring it out in front, just so I don't have to carry it around while I'm integrating with respect to x. If I integrate x squared, I get 1/3 x cubed, where x ranges from square root of y to 3. When I do this inside integral, I should get rid of all of the x's, but still be left with y's. And then I can do the outside integral with respect to y to get just the number. And here, when I plug in x equals 3, I get 3 cubed over 3. So that gives me, I guess, 3 squared minus, when I plug in x equals square root of y, I get 1/3 x to the 3/2 power. Sorry, not x to the 3/2, y to the 3/2 power. X equals square root of y. So y to the 3/2 power dy. Now I just distribute my y. Don't forget about this guy out here that needs to distribute through. And now I can do the integral again. We're back to just the Calc 1 integral. So y to the 5/2 integrates to y to the 7/2 times 2/7, and going from 0 to 9. Trying to get it to not keep jumping me over there. There we go. I see that if I plug in y equals 0, everything zeroes out. So I just have to concern myself with this upper bound. 3 squared over 2 times 9 squared minus 2 over 21 times 9 to the 7/2. And what do I see here? I get 9 squared is 3 to the 4th, so that's 3 to the 6th over 2 minus 2 over 21. Square root of 9 is 3 to the 7th. Times 3 to the 7th. So this is 3 to the 6th times 1/2 minus 2 over 7. Or this 3 to 6 times, 7 over 14 minus 4 over 14, or 3 over 14, 3 to the 7th over 14. And that looks like exactly what we got before. But we saw that the computation on the right-hand side, going kind of rows first, then integrating with respect to y, that computation was just a lot more annoying and messy than doing columns first and then integrating with respect to x. This was just much cleaner, just the way that it turned out. So the way that we choose to integrate when we have non-rectangular regions is of even more consequence than when we have rectangular regions. A lot of times in rectangular regions, it's, maybe a bit of a pain to do it one way or a bit easier the other way. When we're in non-rectangular regions, a lot of times it's extremely difficult or even practically impossible to do it one way and doable or even easy the other way. It is important to note that swapping the order and saying it's impossible to do this way and easy to do that way doesn't mean that it's theoretically impossible. It just means that I don't have a practical integration method that I can use to get the answer. The answer would still be the same, even if I couldn't figure out a nice integration method to actually uh, show me that that is the answer. So it's not that it's a theoretical problem, it's that it's a practical problem. Can I practically actually do the integral and get a nice answer out of it? Um, and often the answer is no, one direction, and yes, the other direction. Okay, so for the last couple minutes here, we're going to look at this problem. I think we can do this pretty quickly. I did have a couple others here that I'll just kick to the supplement, and we'll do those along with, again, some fill in from a little more of the material from section 1 and some extra material from section 2. But we should be able to get through this problem in just a couple minutes. But here again, and you can try to do this integral as it stands, but we have to integrate square root of x cubed plus 1 dx. And that's not a very easy integral to do. We might be able to figure out a way to do it, but it's certainly not going to be nice to do. What happens if we reverse the order of integration? Well, first I have to figure out what is the region that I'm integrating over. Well, y goes from 0 to 4, and x goes from root y to 2. So x equals root y is the same as y equals x squared. So x goes from this curve up to x equals 2. So x is going from root y to 2. So when we're integrating along x, doing those horizontal cross sections first, we go from root y to 2 in the x direction. So that's something like this. And we are adding these up as y goes from 0 to 4. So this is my region of consideration, very similar to the last one. If I want to switch and do vertical integration first, kind of get vertical cross sections, and then add those up horizontally, what does that look like? Well, now y starts at 0, starts at y equals 0, and goes to y equals x squared. Note that this happened to be in the bottom, the bottom limit of the dx integral, and that's the variables in the top limit of the y integral, just the way that it turned out here. And then x would go between x equals 0 and 2. So we could say that this integral is equal to the integral x goes from 0 to 2, y goes from 0 to x squared of root x cubed plus 1 dy dx. And now if we do this integral, we notice that this integrand is just a constant in y. So this is just like a constant. So if I integrate a constant dy, that's just upper bound minus lower bound times that constant, or just x squared minus 0, times this thing that is effectively a constant. So now we've done kind of our column sums, or we've in a sense taken vertical cross sections and computed those little cross-sectional areas. And then we want to stack them horizontally, going from x equals 0 to 2. And that's what this integral does. But this is actually just a pretty nice little substitution. U equals x cubed plus 1 du is 3x squared dx. Du over 3 is x squared dx. So this is just the integral of root u times 1/3 du. And when x is 0, u is 1. When x is 2, u is 9. So we get 1/3. U to the 1/2 integrates to u to the 3/2. 2/3 of that from 1 to 9. And this is 2/9 times 9 to the 3/2 minus 1. We could simplify that, but we are out of time. So we'll just stop there.